Now we will continue with source coding with typical sequences. We look at the following model. We have a discrete memless source which emits a string xn of symbols that are passed to an encoder. The source encoder puts out an index w and sends w to the decoder. And the decoder reconstructs w as x hat of n of w. And the decoder is, of course, successful if x hat n of w is equal to xn. So we denote now by L of xn the number of bits transmitted for xn. So the goal is to minimize the average rate, that's the expected value of L of xn to n. So we can do the source encoding in several ways. The first thing is we can assume that we receive a block of words from the source and decode it and encode it into a block. So W is also represented by a block, or we will have a block again of the source, and the source encoder puts out some variable length codes. And these two cases we will consider, but there are several more cases. Of course, we can assume that the source puts out some variable lengths and it will be encoded in a block code, or we go from variable length to variable length. So let's look at the first situation. So we look at block to variable length encoder. So, and the main idea is that we treat sequences differently depending if they are typical or not. So the idea is if the source puts out typical sequences, then the encoder sends a 0 and followed by a string of bits that represent xn. We know now by our theorem what we had, independent which we use here. We use this for letter typical sequences. We also could have used it for entropy typical sequences, but both gives us that we can represent W by n times 1 plus epsilon times the entropy of x bits. So that means we send a 0 and then n times approximately the entropy of x bits, which represent xn. If if the source puts out a non-typical x to the n, then we just send a 1 and followed by n times log 2 x bits. So much more bits than we need, but it's enough because this case is very seldom that it puts out some non-typical xn. So then we just use a binary representation of the source sequence. So the idea is that xn is typical with very high probability. And we know that there are 2 to the n of the h of the entropy of x such sequences, and we can represent them with 8 entropy of x bits. In fact, if we now calculate it and use our theorem, so we look at the rate, that's expected value of L over n. So this is equal to the probability that the sequence is typical and plus the probability that the sequence is not typical. Here. And now we know, if you look how we encode this, that this length here, in the case that the sequence is typical, is equal to 1 plus epsilon times the entropy of x plus 2 over n. So this one is over this here. So this should be in brackets perhaps. The 2 just comes from, because of the rounding, we have 1 bit more, and because we sent some additional bit to signal the 0, that we send now typical sequence. And the same here, if we send a 1 and then log 2 of x and over n. Now if we look at this, we can estimate this by 1 plus epsilon at entropy of x plus 2 over n plus delta epsilon px of n times log 2 of x plus 2 over n. This is just the estimation of the cardinality of the typical sets here, or sorry, of the probability of the typical sets. We already know this probability goes to 1, so it can be upper bounded by 1, and this probability can be upper bounded by this delta epsilon. But we know delta epsilon goes to 0 if n goes to infinity. And now what happened for big N? So we see here it remains 1 plus epsilon times the entropy of x. So that means we can transmit at any rate above the entropy of x as we expected. Now we look at the second case, that's block to variable length encoder. So we use the same idea in principle now. But we have the advantage, now we don't have the same length for each code word. We can use variable length. So again, we use this idea that with high probability, the sequence which is put out by the source is typical. And if it's not typical, we just map it to some sequence, so we know that there will be an error. So what we do, we reserve the all 0 sequence. So therefore, we can bound the rate by 1 over n, and now we have n times 1 plus epsilon h of x, and we have this one all 0 sequence here, plus 1. And if we estimate this, we get here 1 plus epsilon times entropy of x plus 2 over n. And the error probability again is bounded by delta epsilon of delta epsilon. So again, we can send h of x symbols. But what is about the converse? Is the entropy of x also the best possible? Or perhaps one can transmit less symbols than the entropy of x and already achieve a small error probability. And this is a proof you know it from information theory. So I will really go on it, and perhaps you will recognize that you know it. What we use is a Fano inequality. So the Fano inequality says if PE is the probability that the estimate of n is not equal to x to the n is denoted by PE. Then the entropy, the binary entropy of PE plus PE times the logarithm of x to the n minus 1 is greater or equal than the conditional entropy between xn and x hat of n. We will use the Fano inequality also with this by removing this minus 1. It's a little bit weaker result, but it's enough for this case here. So we can recall that we have at most 2nr different sequences. That's exactly how we define the rate, that we have so many sequences x hat to the n. And x hat of n is of course a function of xn. So because we have just so many sequences, we can bound n times r by the entropy of x hat to the n. That's just the normal bound here. It's very simple. And now we know, of course, x hat of n is a function of xn, and from information theory, you know that this is then 0. So we can just write here minus h of x hat of n conditioning on xn. But this formula, you know, this just gives the mutual information between xn and x hat of n. And now we do this trick and write it in another way. We know because this is somehow symmetric, we can also write it at h of xn minus h of xn conditional on x hat of n. Now this we can write because they are as n times h of x minus h of x xn hat of n. And now we insert for this term here, we use the Fano inequality without this minus 1 here and put this in. And then we get here n times h of x minus h2 of pe over n minus pe times log 2 of x. So we know log 2 of x is a constant. Pe is small, it should be 0 if n goes to infinity. And this term goes also to 0 if n goes to infinity. So we are remaining, so this term, this term h2 of pe goes also to 0 if pe goes to 0. So we remain with n times h of x. So the entropy is really also a lower bound for the rate, and the proof is done.